Thank you. Thank you. All right, thanks everybody. So I'm going to give this talk. So this is some work that was joint with my student Charlie Kurtzinger, who's now at Grinnell College, which is a liberal arts college in Iowa. No counting for taste. Anyway, all right. So I'm going to start with a story. So this story took place a few months ago in a valley far, far away. You'll probably recognize the valley soon enough. This is Bob, and Bob has an idea for a startup, right? So here's Bob's genius idea for a startup. It's going to be an app, of course, and so the app is going to work as follows. You take a photograph of something like a cat, and it goes and finds matching pictures of cats and sends them back to your phone, all right? He even has a snappy name for this startup. He calls it Ogle. Right? And he's convinced that this is going to totally disrupt image search. So, nobody has told him that Google also does this, but that's okay. All right, so he's pressing forward with his genius idea. So here is the architecture for Ogle. The way it's going to work is that people will take pictures of cats, of course. These will get sent to the Ogle servers. The Ogle servers will actually store the images. So there'll be more and more images as more Ogle users come online. And then it'll go find whatever images have been uploaded before that resemble this image and send the results back to the phone. All right? So at a very high level, you can view this as follows. There's sort of two threads of control. One of them goes and compresses the images or downsamples them or something. It saves them using this icon, which will cease to have any meaning for anybody in this audience soon. And at the same time, it'll do feature extraction. So it's going to go ahead and take the image, do some processing, extract core features, do a search to find all the similar images, and then send those back. And of course, these two threads basically join at the end. All right? Of course, being a multi-threaded application, you can't just run these threads simultaneously. You need to impose locks so that the database remains consistent and so on. All right? So pretty basic. All right, so Bob fires up Ogle, and Ogle naturally, you upload an app to the AppStore and millions of people download it immediately, so it's working out great. And then he discovers, to his chagrin, Ogle is going really slow, right? It's running really slowly, so that's not good. So here is a different Bob. This is Bob, but Bob in the 80s. Notice the glasses. Which are coming back in style, apparently. All right, so Bob in the 80s, of course, didn't have phones. This was his device, was a big thing, with a big monitor on a desktop. And the graphics weren't quite as good either, right? So there's this image of a cat. Things were obviously a little older back then. There was no great user interface, no web pages. You got these, this is sort of your user interface for those of you who remember 80s style applications. You get all of your results, and great, he has a great 80s name for it. It was GraphoSearch. All right. So, back then when Ogle was, he says Ogle's too slow, this is today. Bob also had problems back in the 80s, right? Computers were slower. So the thing is that this is a graph that will be familiar to everybody here, right? So on the left we have transistors, and on the right we have clock speed, and as you can see, things were going pretty smoothly, classic log scale curve. You all know how this worked. So things were really terrific a while ago, because as things got smaller and smaller, they got faster and faster, right? So this is popularly referred to as Moore's Law, but really it's Dennard scaling. But the upshot was all you had to do was buy new hardware, right? Every year or so, you would just buy new hardware, and your code would run faster. Right? So your job as a programmer when you're trying to make your code efficient was actually a little bit different. So this is the way you would do performance analysis in the 80s. You would kick back on the beach, sip a mojito, for example, and wait 12 months, and then people can just buy new computers and things run twice as fast. And this is a lot better than the alternative, right? So unfortunately, in the present, Bob doesn't have this same luxury. Right? Because now when you buy a new computer, the new computer is just newer. It just has less dust on it. Maybe it has longer battery life, but everything plateaued. And so the problem, of course, everybody knows is that things just got too hot. right? So transistor counts are continuing to increase. Moore's law hasn't really stopped. And so what's happened, of course, is that the transistors have basically been turned into more cores, right? So now the task is much harder than it used to be. You didn't have a core that was just getting faster and faster. Now we have more of them, right? So those are different cores. And so really all you have to do is just write multi-threaded code that's efficient. Problem solved. Unfortunately, that's really hard. So, these processors are great little processors, and we have a bunch of them, but they're hard to program. So how much of a problem is this? So I actually took a bunch of screenshots from my phone. So these are app updates from the App Store. You can see this says bug fixes and performance improvements. And then this one says bug fixes and performance improvements. And then this one says bug fixes and performance enhancements, which are maybe better than improvements. It's not clear. Again, performance improvements, and so on and so on, right? The usual performance enhancements, performance and stability improvements, and so on. So it turns out that every single one of these updates practically is an update that is focused on fixing bugs and making things run faster, right? So why is this hard? You would think, oh, well, this is really not so hard. Well, the problem is that actually taking advantage of these cores and programming stuff to be efficient is pretty tricky. So I'm going to dig in a little bit into why this is tricky, right? Why is this so hard? It doesn't seem from the outset like this should be such a hard problem, but if it weren't a hard problem, we wouldn't have update after update after update saying, hey, we made the thing a little faster, a little faster, a little faster. They just would have shipped faster code, right? So what's the problem? So it turns out that compiler optimizations have kind of run out of steam, as I'll explain. Hardware is not automatically getting faster for us. Performance analysis approaches turn out to be unsound, which means it's actually difficult to identify what the source of a performance problem is. And performance profilers are basically mired in the 80s, back with old Bob. All right, and they really haven't caught up with modern architectures and modern software architectures either. All right, so let me dig in. I'm going to talk a little bit about performance analysis and why it's unsound. So basically, it turns out that for many, many years, when we've been doing performance analysis, we've accidentally been doing it wrong, right? And the reason we've been doing it wrong is that memory layout now has this huge impact on performance that was not necessarily obvious. And so this is unfortunately something that is it's very difficult to disentangle. Anytime you change a program, you change one line of code, you put in one more statement, you have changed the memory layout of the code itself. And if you allocated any memory, you've also changed the layout of all of the objects on the heap. And this can have a dramatic impact on performance. So what this means is that there's no way to measure this change in isolation. As soon as I make a change in the code, I do a little, I move this function around, I allocate one more object, now everything has changed. What's the performance impact? Was it because of my code? Was it because of the layout? It's difficult to disentangle this. So we built this system called Stabilizer that eliminates the effect of this, enabling sound performance evaluation. So I'm going to walk through how Stabilizer works, really dig in a little bit into what the problem is, and then I'm going to talk through some case studies where we actually went and applied Stabilizer to evaluate LVM's optimizations. And the news is not good. All right, so let's go and explain a little bit about why memory layout affects performance so much. So here's a program. It's a real program, but it's actually Stabilizer. But you don't care. It doesn't matter what the code is. The point is we're going to make some changes to this code. So we're going to call this version of the program version A. Right? And now I'm going to go and I'm going to refactor some things. Maybe I move a function to a different file, right? I break out some stuff, I inline some things, and so on and so forth, trying to make the thing faster. And now I have version A prime. All right? So now I run my program before and after, and I get a graph. And the graph looks like this. I'll zoom in. So this is version A. It's about 90 seconds. And this is version A prime. It's about 87.5 seconds. All right? So is A prime faster than A? How many people think A prime is faster than A? Raise your hands. Okay. All right. How many people think that A is faster than A prime? All right. Good. Just checking. That would be strange. Be like, you can leave. All right. So you can see, right? Obviously, this one is 90 seconds. This is 87.5. Right. This is less than that. So we conclude oh, clearly A prime is faster. We're geniuses. This worked, right? We shaved 2.8% off of the execution time. Is there any problem with this approach? Yes.
It's a single run.
It's a single run. What's wrong with that?
Unless it's fully deterministic, different runs can get different results.
Well, so the code is deterministic.
Also warm up the caches.
Okay. So we have to warm up the caches. What else? I heard something else. Storage, right. So maybe there's something with the storage devices. Anything else?
It's running by itself.
It's running by itself, so there could be interference, right? So really all this comes down to is variance, right? So what is the variance here? We have no way of knowing because we only ran it one time. All right, so how many times should we run it? 30. 30. Done. Well played, sir. Well played. So 30, it's not a magic number, but...
What base?
Sorry?
What counting base?
What counting base? Base 1. All right, so we do it 30 times. 30 is a ridiculously large number of times, it turns out, but that's okay. The computers are fast. We have time. So we run it 30 times, and this is the variance that we observe. This is actually the distribution of runtimes. All right, so now I'm going to ask the same question again. Is A prime faster than A?
Your machine.
Yes. Yes.
Yes, it is.
Yes, it is. Okay? All right, so why? Why is it faster? All right, so it's possible that I actually optimized the code. Stranger things have happened, right? But it could also be that just by sheer luck, when I moved the code around, this actually changed the memory layout in a way that benefited performance. Right? So how could this happen? So it turns out there's this very fun paper that appeared in AskPLOS 2009 by Todd Mitkowicz, who's now at Microsoft Research, Amr Dewan, who's now at Google, and Peter Sweeney, who's still at IBM, and Matthias Hauswirth, who's at Lugano. And so what they did is, they took some code and they did the following things. They took the make files and they reshuffled the link order for the .os. Right? That's all. They also changed the size of the environment variables. So they literally said, export foo equals xxxxx, right? And that increased the size of the environment variables. So why does that matter? So when you change the link order, it's moving the functions around. So the addresses of functions change, right? The addresses of all the code completely shift. The environment variable size, weirdly, on Unix-based operating systems, when you load a C++ or C executable, it actually copies in the environment into a buffer, and then the stack starts from there. All right? So it shifts the position of the stack, which shifts the position of all the stack variables. And this impact of just doing these things is larger than the impact of -03 on the code. So in some cases, it led to 40% performance improvements or degradations, which is... it should give you a little bit of pause, right? So what is going on here? So first, the obvious problem is the cache. So if I have code, and this is a hot piece of code, and this is a hot piece of code, these map to the same cache set. If I fill up the cache sets, right, I'll end up with conflict misses, right? So now I'm degrading the use of my cache. If, by luck, when I reshuffle these things, I end up with no conflicts for the code, suddenly locality improves, all right? What else can happen? So what else can happen is that we can end up with branches that unfortunately alias, right? So if I have a bunch of branches that alias, and if they're destructively aliasing, and they land in the same place, so I have one that says always taken, one that says not taken, suddenly becomes 50-50. This is no good. Now I'm going to misspeculate. What else can fail? The TLB. So if I have things that are spanning a bunch of pages and then they end up in a smaller set of pages, suddenly performance can improve, or vice versa. Anything else you all can think of? All right, so it turns out there's a whole list. So caches, branch predictors, TLB, branch target predictors, prefetchers. All of these things depend on the addresses of memory. Right? So the addresses of memory are used as basically arguments to a hash function. And so if you have changes in memory, these affect the values that come out of the hash functions, and these affect all of these structures, these fixed side structures in chips. All right, so that's too bad. All right, so let's talk a little methodology here. So when we say is A prime faster than A, what we do not do, like in sort of science, let's say, pretending for a moment that's what we're doing, we don't, like if we're doing a poll of people, imagine you're doing a poll. Like I'm going to survey you. I'm going to say, hey, I would like to know something. So I'm going to give a survey. Do I give a survey to one person? I do not give a survey to one person. That's stupid, right? Because you get the same answer every time. But that's kind of what we're doing, right? We're taking some code, and that code is running, and then we ask the code, are you faster? It says yes, 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 right? So why is it faster? Well, it's faster maybe because the code is faster, or maybe because of the memory layout issues I described earlier. What we really want to know is we want to ask a bunch of different people, right? When we poll them, we don't ask one person, we ask a bunch. So the same sort of thing is what we really want if we want to understand if the code is really running faster. I want to see if it runs faster across a range of different likely memory layouts or possible memory layouts. So at this point, a number of people might think, well, I don't care to hear other people's opinions. I just want Bob's opinion. Bob says it's faster. Faster is good. I like Bob. All right? So why don't we do that? Let's listen. We run it with Bob's layout. And maybe the code change improved performance. Maybe it was the memory layout. I don't care. It's faster. Good enough for me. Seems maybe reasonable on its face. So what this means is, well, we're just going to use one memory layout. So what is this? That seems fine. All right, we got this memory layout. Terrific. What can go wrong?
Fix a bug.
Sorry?
You fix a bug.
You fix a bug. So why is that a problem?
Along with the same layout.
Yeah, so if you fix a bug, if you do anything really, you're going to end up with a different layout. So the layout is going to change as soon as you change the code. But it can happen in even more subtle ways. You don't even have to change the code. So for example, if you upgrade a library, the library is going to almost certainly have different amount of code in it, and that's going to result in shifting everything in memory. Maybe it's going to result in more memory allocations, which will again shift things in memory. All right, here's a fun one. What if somebody else uses your software? It's not just you, all right? So remember I said that the environment variable size actually affects where things get laid out. So this actually happened to me. I had a student who went to implement an optimization. I knew it was going to speed things up. I knew it. I told him it was maybe 10, 15%. It's going to make a big difference. Huge. There's somebody here I have to channel for a second. Huge improvement, 15%. I'm sorry. So anyway, he went and ran the code, and he was very polite, very nice guy. And he came back and goes, I'm really sorry to tell you this, but it turns out that it runs slower. And not just a little slower, 20% slower. So that makes no sense at all. You're clearly doing it wrong, right? And we went back and forth, back and forth. I looked over all the code. Yes, he was implementing it correctly. Everything looked good. And he ran it on his machine, 20% slower. And I ran it on my machine, and it was 15% faster. And I said, it works fine for me. So we ended up both at my computer, and with one login window for me and one login window for him. I add in passing that he is Indian. This becomes relevant in a moment. And so his thing, like totally quiescent. Everybody is off the machine. In his window, 20% slower. In my window, 15% faster. I then SU'd as me, and it was 15% faster. Why? Because he has a long username. And my username is 5 characters. So obviously the solution is everybody should have 5-character long usernames, right? It turns out, unfortunately, there are other weird things that happen in your environment, like days change for some reason. So Monday and Tuesday are shorter than Wednesday. And this is actually something that would lead to timing for like noticeable performance differences depending on the day of the week, which is, it's nice that it happens on Wednesday, right? Because you're like, things are good, oh God, why? And then things get a little better, and then Friday it's back to normal, and you're like, okay, perfect, time for the weekend. All right, so this is all super brittle. Even stupid stuff like running in a different directory changes your layout, because a directory goes into your CWD variable. And so a long directory string might be really good or really bad. This seems a little weird. All right, so layout is super brittle, and picking like this is faster because the layout worked out, it's not going to work out well if you really, unless you do nothing different ever, including, like time doesn't move, so dates never change. All right, so now the question is, can we actually eliminate the effective layout? So why do we want to eliminate the effective layout? This is really brittle, it messes with performance, but it also means we don't really understand what's happening. Right? If I make some change to my code and it runs slower, is it because I actually caused a performance regression, or is it something that's going to go away on Wednesday? Right? That's what I want to know. So the answer, of course, is yes, we can change the effective layout. And so I'm going to explain to you how we do this, and then how we can leverage this to do sound performance evaluation. So Stabilizer is the system that we built. Stabilizer is, at heart, a system that randomizes everything. So what it does is it randomizes function addresses. So every function is potentially at a new location. Stack frame sizes, which effectively randomizes the objects on a stack, and even heap allocations. All right. Now, in addition to randomizing things, Stabilizer actually randomizes them repeatedly at runtime. So it's constantly re-randomizing your program. Right. So what does this mean? It means that because this is happening during execution, there can't possibly be a bias because everything is randomly changing. It's essentially marginalized out, if you will. All right, a completely random layout can't bias results. All right, so now let's go back to this performance evaluation we did before. And now we're going to run it with Stabilizer. And what you're going to see is you get different distributions. Why are you getting such different distributions? I'll explain a little more in depth in a minute, but you can just intuitively think, well, I'm exploring much more of the space, so I'm going to experience more variance. All right? These look suspiciously like normal distributions. There's a good reason for that, and I will explain why in a second. All right, so now I'm asking the same question. Is A prime faster than A? How many people think A prime is faster than A? Raise your hands. All right, keep your hands up. All right? All right, is it faster now? Just, all right, a few hands are going down. I like the hands that are like, all right, how about now? All right, a few brave people. Okay, so why? Why did your hands go down?
It's not statistically significant. You're asking the wrong question.
Yes, okay, so you're both right, all right? Okay, so it turns out this is not actually how stats works. And so somehow we lose sight of this sort of thing. This is the wrong way of evaluating things. By the way, this is referred to by statisticians as the eyeball test of significance. And that's not a real statistical test, right? So what we actually are supposed to be doing, at least in traditional statistics approaches, like the statistical significance thing that you just asked, what you do is you adopt this null hypothesis test, right? So you say, pretend that both things were the same. Right? So if both things were the same, what would be the likelihood that by random chance we would have observed this difference? Right? And so if the difference was really, really large, then it's probably very unlikely, right? And we can quantify the unlikelihood or likelihood as a p-value, all right? So this probability, by the way, is super easy to compute for the normal distribution. This is not critical, but it turns out to be very nice. So you probably have seen this at some point in your lives, right? So here's in a normal distribution, right? You have these things that go out to the tails. Here's your mean. And as you get further and further from the center, right, it gets less and less likely. All right, so what we're going to do is we're going to do sound statistical analysis of performance. We're going to say, what is the probability of measuring a speed up this large by chance? And then conclude, if the probability is low enough, for some definition of low enough, then this speed up that we observe is real. And because we're using Stabilizer, we know a priori it can't be due to layout, right? Because we're constantly shuffling the layout. So this is really a randomized experiment. So you remember that I said that it repeatedly randomizes layout. So let me explain why this is crucial. So this is, these are actual execution times of some code where we did run one random layout per run. Right? When we did the randomization, all of a sudden you get this distribution, which turns out to be normal. So why is this a normal distribution? So this is how Stabilizer works. So Stabilizer has a parameter, which is its frequency of generating random layouts. Its default is a half second. So for code that runs for any reasonable length of time, this is a lot of random layouts. Let's say at least 30. We all like 30. All right. So the total execution is obviously sum of all of these half-second periods. And it turns out that the sum of a sufficient number, let's say 30, of IID random variables is in fact approximately normally distributed. So this is the central limit theorem, which means that when you run code with stabilizer, the execution times end up following this normal distribution. Now I hasten to add, you don't need normal distributions to do sound inference. All you need is randomization. All right, the normal distribution is not required, but it makes the statistical analysis very powerful. All right, great. So now we have this in hand. So now we're going to use stabilizer. So here's what we decided to do. Let's assume, for the sake of terribleness, that compiler optimizations do nothing, that they don't help at all. We sure would like to reject that hypothesis, right? Because, you know, I don't know, I like my code running faster. I like being able to say -o something and code runs faster. My favorite is that every now and then you run into code, open source projects, which have -09, which is just so cute, right? Like people are just like, that is optimism. Like there is no -09, but maybe someday, just make my code faster, please. All right, so here's what we did. So we ran LVM's optimizations with stabilizer on every benchmark and across the whole benchmark suite. So first, of course, you have to build the benchmarks with stabilizer. Stabilizer is an extension to LVM, and so you can just compile your code instead of using, you know, CC or Clang. You say SZC. If you only want to randomize a particular thing for some reason, like I don't want to randomize the heap and the stack, you can just say I just want to randomize the code. This is the default. All right, now we run the benchmarks. We get our results. We do it 30 times, and then we drop the results into R. And of course, this is the question we do not ask, right? Instead, we ask this question, right? The null hypothesis test. If they are the same, what's the likelihood of measuring a difference at least this large? And it turns out that we just can use the t-test for a small number of samples. So this is the R code for doing this conveniently, all right? And we're going to adopt, let's say, we're going to use the rigorous standards that social science is known for. And use their p-value threshold, which somebody said 30 before. I'm going to give somebody another chance. What's that p-value?
95.
Yes, 5%. Bingo. All right? So somebody knows this game. All right? So we're going to use 5% as our threshold. So that means that, you know, if we observe some difference, it should be less than 1/20 likelihood that it actually happens by chance. All right? That's what that means. All right? If that happens, then we're going to reject this null hypothesis that they're the same. All right, that is to say random chance is not responsible for the difference. It is a real difference due to an actual improvement in the code, which is sort of what you'd like to see. So it turns out -01 versus -0 makes a huge difference. Honestly, the eyeball test is good enough. It makes a big, big difference. All right, it's not too surprising. -0 does practically nothing. -01 actually has optimizations like, you know, like 1957 through 1963 level optimizations, which turn out to be pretty important. All right, how about -02 versus -01? So this is actually all of the benchmarks from the latest spec, and this is speed up to 20%, and the bars are green if it's statistically significant, and red if not, and these are confidence intervals. And so you can see some of the improvements are really huge, right? Huge. So 20%. This is not statistically significant out over here, unsurprisingly, and we got statistically significant slowdowns. So it turns out that using -02 for live quantum actually slows your code down by about 8%. And this is definitely statistically significant. All right, great. That said, most of them improve execution time, right? They actually speed things up. So hooray, -02 is better than -01. On to -03. All right, that's -03. We're gonna have to zoom in. So let's zoom in. So now this bar is no longer 20, it's 1.5%. And you can see that yes, we do get some statistically significant improvements that are maybe not quite huge, 1.5%. We get a lot of stuff that is not significant anymore. And then we get a few statistically significant, very minor degradations. All right, so what do these results mean? So these results only tell you something about individual benchmarks. This is not really something that you should use as a test, like some are insignificant, some are significant. Or is it a significant increase? Is it not? It's not obvious, right? So what you're really supposed to do is what we are now going to do. We're collect all of them and put them together. And instead of looking at each one individually, right, and saying, hey, this one is slower, these are faster, 2 out of 3 ain't bad, right? That's not the way we're going to do it. Instead, we're going to use a similar approach, but across multiple things. And so here we use ANOVA, right? So an analysis of variance. Here's the R-GOR for computing this. Again, if the p-value is less than or equal to 5%, we're going to reject the null hypothesis and say, okay, these optimizations actually made a difference. All right, how many people think that they made a difference? Wow. All right. How many people ever used -03? See, what's going on? All right, this is just optimism. See, and they say that Israelis are cynical. And it's clearly not true. All right, so it turns out that the p-value here is 26.4%, which is pretty far from 5%, right? This is essentially saying, are we 73.6% confident that this thing is not due to random chance? I know. I know, it's a folk way of describing it. Really, it is that the likelihood of observing this difference is 1 out of 4, right? So 1 in 4 experiments will show an effect that doesn't exist, which is not good. All right, so we're going to reject the null hypothesis. We're not going to reject the null hypothesis. The null hypothesis says that the two are identical. So for now, we have to say -03 versus -02, effectively indistinguishable from random noise. All right, I'm going to gloss over this really quickly. There's this question of whether stabilizer hid the effect. So stabilizer actually adds basically a constant overhead to functions, which is a trampoline for every function. So you get this sort of constant increase. And this constant increase is unbiased, so it doesn't have any effect on the statistical results that we just presented. All right, great. So, as I said, memory layout affects performance. Stabilizer fixes this. -03, not statistically significant. Oh well, what is Bob to do? So what Bob unfortunately now realizes is when he compiled his code with -09, it didn't help. So he actually has to get down and do some work, right? So what should Bob do? Profile, all right? Use a profiler, exactly. So we go and we take our handy software profiler. You pick one. Profilers basically work the same way. They gather information about the number of calls to every function. They gather the runtime for every function. And then the idea is, well, you find the things that take the most time, that run the most often, and you focus your optimization efforts on that. All right? So what that corresponds to is frequently executed code and code that executes for a long time. That's what you should be targeting. Obviously, if you think of the inverse, right, code that never runs, that code doesn't need to be optimized. So you think, okay, this is good, right? So this seems like this is really a good guide to where Bob should be spending his time optimizing his code. So Bob goes and he uses his profiler and he says, hey, this thing is loading really slowly. So he goes and he optimizes the hell out of the thing that is running for a long time. It's super frequently executed, runs forever. And this is the result. So what happened? It didn't really speed up Ogle. It just made load blink faster, right? That is very frequently executed code. And it runs for a long time. It, in fact, runs for the longest time, right? It runs from the start to the end of every single transaction. But that's not really great. That's not what we wanted. And really, the takeaway here is that profilers don't do a great job of finding important code in parallel programs. So we need better tools. So the question is, what would speed up Ogle? So if you look at this code, you would kind of like to know, hey, show me the place I'm supposed to go optimize my code. So if we had some sort of like magic dust that we could sprinkle on the whole program, hopefully it would just stick to the parts of the code that actually mattered, and then you go, oh, that's where you're supposed, okay, Bob says, oh, right, I have to optimize this, and that's going to speed up the code. All right, so what would this information look like? So maybe having, sparkly bits on your source code is not particularly helpful, right? You maybe want to know something a little more granular, and that's not so sparkly. So here is this idea that we have, we call a causal profile. So causal profile tells you exactly where optimizations make a difference, but not just where, but how much. All right? So here the x-axis is how much you speed up a particular piece of code, and the y-axis is how much you then speed up the program. All right? And what we're going to want is a graph that looks kind of like this. So this is going to quantify how much effort I have to spend optimizing something, and then how much return I get. So it's a bang for the buck curve. All right? So here it says, boy, if I optimize this search part, wow, things get better, and once I get to here, stop. Right? It's not going to make the program run any faster. Right? With this compression part, it turns out that it's not on the critical path for anything, and speeding it up doesn't make a difference. Meanwhile, this feature extraction thing, it's not as big of a bang for the buck as the yellow one, but it kind of keeps going. So that's nice. All right? So all this tells you is if you speed up your program by this amount, then you get this result back for your speed up. All right? Great. So how are we going to get this graph? So how would we know that this change caused this effect? Well, one way we could do it is we could just run an experiment. So we're going to run performance experiments, and it's going to require some magic, because magic is awesome. All right? So we're going to use some magic, and what we're going to do is we're going to magically speed up this piece over here, the search, and then we're going to observe a difference in execution time. And we say, hey, that sped up the program by this much. And then we can put a dot on the graph, right? And we do it again, right? And then we see a larger speed up, and eventually it'll run out of steam. We can do it for every single piece of code. We do it for the storage part, doesn't speed up the program, and so on, right? So far, so good. There's only one fly in the ointment here, which is that magic, prepare yourselves, magic is not real. I know, I'm sorry. But the Easter Bunny totally is. Okay, so no magic. If we had magic, by the way, this is the stupidest thing you would ever do with magic, right? So, I mean, obviously, I don't know, wings, world peace, things like that. But also this, right? Just speed everything up to 0, right? That makes the most sense. All right, so we're not going to be able to do this. So here is the trick. Illusion. So the illusion here is that we're going to speed things up, and the way we're going to speed things up is we're going to slow everything else down. Taking a page out of Einstein's book here. So what we can do is we can say, I'm going to get the effect of speeding this thing up by taking everything that's running concurrently with it and slowing those things down. So relatively, it will run faster, right? And then I do a little bit of math to compensate for this slowdown, and I capture some amount of speed up, right? So now I can actually go and compute these graphs by going and slowing something down by speeding something up virtually by a certain amount, which means slowing other things down by that amount, right? And I do it again, right? Slow this up, and I get this result, right? I can do this for every single component, right? Every time this runs, I pause all the other threads, I get a result at the end, and I put another dot on my graph, right? So on and so forth. Here, when this runs, I pause all over threads again, I slow this down, I get a little bit of nothing, right? Nothing happens, and I keep going, and suddenly you notice the lock acquisition order changes, which is exactly what would have happened if I'd sped this thing up. And so now crazy things happen, like, for example, this, right? So what happened is that actually speeding that component up would be bad because it causes more contention, it messes up the lock schedule, and leads to worse performance. So you definitely don't want to touch this blue code at all. All right? So you gather all of the stats for every single thing, right? Eventually this comes back up. Clearly, if you think about it, say, well, if I achieve, let's say, 90% performance optimization on this piece of code, finally I get this little bit back, probably not worth the effort, big risk of, it's hard to optimize things by 90%. All right, so these graphs can be quite useful. So of course, now we're going to apply them to Ogle. Now Ogle, runtime is not really meaningful. So if you think about it, like end-to-end execution time of your browser, you don't really care how quickly your browser exits. We can make that really fast, right? Just put abort in there. What you really care about are things like, for example, how quickly results come back. Right? So you care about throughput. You also care about the time between starting a search and getting your results, that is to say latency. Right? So traditional profilers really have nothing to say about these things. They only care about end-to-end execution time. But really that doesn't make sense these days. So the way that we're going to deal with this is we're going to as programmers, put in these little tiny annotations that we call progress points. So for example, suppose I just want responses to go out faster. I want more throughput. So we're going to mark this as a progress point. And every time that code runs, we increment some counter, all right? And we say, oh, we got more of them. So if we get more of them faster, then we're improving things. That's our dependent variable for our experience, right? So as we run a bunch of threads doing all of this stuff, we'll get many requests for many users, right? They'll hit all the progress points, right? And each one is going to measure all the throughput, and then we'll be able to actually quantify what the effect is of the code on throughput. Likewise, for latency, if we want to minimize response time, you add 2 progress points, one at the beginning and one at the end, right? So now, as new transactions come in, it increments a counter. When they leave, it decrements a counter. And it turns out that through a judicious application of Little's law, we can actually recover the latency because we have this count of transactions, and then we'll measure the throughput using the progress point thing I mentioned earlier. All right? So we built a causal profiler for Linux. It's called Cause. So Cause you execute like this, Cause run .. and then your program, sort of like running Valgrind. Cause is actually going to be shipping with Debian in its next release. You can get it in the unstable version today, or you can download Cause from its page. So Cause produces causal profiles. So now I'm going to show you how we use causal profiles to improve Ogle. All right, so we didn't really build Ogle because that would be silly. All right, and kind of a waste of time. But it turns out that a lot of the components of Ogle are off-the-shelf components that you could use to cobble together Ogle. So there's this suite of parallel benchmarks that mostly come from Intel called Parsec. So Parsec actually includes a thing to do image deduplication. That is a form of compression. Image comparison, so it does this feature extraction and search I described earlier. And then there's a database for storing things, so we'll use SQLite. All right? So first I'm going to talk about ferret, which does this image comparison. So ferret is a pipeline. It does the segmentation, feature extraction, indexing, and ranking. Of course, it has the input and output stages. And it allocates some fixed number of threads to each of the stages in the pipeline. Right? So we ran Cause, and these are the graphs that we actually got out of Cause. You can see we get these dots for every single experiment, and then it does a trend line through them with confidence interval. So the interesting thing is that the top one turns out to be in the ranking stage, the middle one in indexing, and the bottom one in segmentation. So this tells us that what we can do, really, we should not be worrying about feature extraction, because feature extraction doesn't show up in the top 3. And we can optimize this code really easily just by stealing threads from the feature extraction stage. So all we did was change the code so that you could plumb through a number of threads that were assigned to each stage instead of a fixed number. This resulted in 21% speed up. All right, not too bad. I should add that this took, and in fact, every single thing I'm going to describe today took about an hour at most for code that we had never, ever looked at. All right, so it's actually super actionable, very, very easy to act on these results. So what did it predict? So ranking, when we increased it from 16 to 22 threads, this corresponded to a 27% increase in ranking throughput. All right? When you do this and you actually look on the curve, you get a 20-something percent, 21% improvement that's predicted by Cause, and this is exactly what we observed. So it's doing great. All right? It's almost distressingly accurate. It turns out that like the law of large numbers works. Who knew? All right, so now let's look at dedupe. This is actually just funny. All right, so here's how dedupe works. So here are 2 images, the kitty cat and the meme version of the kitty cat. All right, so how are we going to do deduplication? What we do is we cut out the pieces of the image that are the same, and then instead of an image being made of one thing, now we add a level of indirection, and so grumpy cat is these pieces, and the one with the meme, the fun is awful, is these pieces, and they have one big shared chunk. All right, pretty straightforward. The way this is done is through a hash function. So it hashes these things into buckets, and it goes and puts all the different images into all of these different buckets, as one does. All right? Great. So, unsurprisingly, this is a multi-threaded piece of code. The hash table is accessed concurrently by many threads. So you might think to yourself, maybe the people who put this together were idiots, and they only had one big lock surrounding the thing, and that was the problem. No, they outsmarted everybody. There's a lock per bin. Genius move. Okay, so here's the weird thing. Causal profiling said that this loop, the loop that searches through the buckets, is important, like pretty important, which seemed weird, right? The whole point of hashing is that there shouldn't be much time spent actually linearly searching this list, right? So we said, all right, well, maybe there's just not enough buckets, right? So we doubled the number of buckets. And then we ran the code again, and we thought, oh, it'll just spread things out, and the problem is solved. This was a very easy change. We just changed a pound define, like num buckets, but it didn't do anything. And we were like, what the hell? All right, so what do you think the problem is?
Image comparison.
What's that?
Image comparison.
No. The problem is here. Hash function, exactly. So we looked at the hash function. So we took a look at this hash function. Before we did, we said, well, let's see what the distribution is into bins. So this is the actual distribution into buckets. So this is the number of items per bucket, and you can see a lot of empty space. So the hash function is super bad. It had a 2% bin utilization, which is not great. Here's what the hash function does. It actually takes all of the, so it takes an image, and it goes byte by byte, and it adds them. So if you think about it, these are basically random values being added together. So it's actually, if you go ahead and you graph this, it turns out it's a perfect normal distribution. It's like a textbook example. It's really a thing of beauty. So we changed one character. We changed the plus to an XOR. That's it. And we got an 82% utilization, and this led to a 9% speed up. So it's not enormous, but it is real, and we found it very quickly. So again, we're in a position where we can actually measure how accurate causal profiling was. So before the average blocks per bucket were 76, now it's 2. This is at 96% traversal speed up, so we actually optimized a piece of code by 96%. And when you look on the graph, it predicted a 9% speed up, which is what we got. All right, great. Finally, we looked at SQLite. So SQLite is this database that everybody has everywhere. You probably have 10 versions of it running on your phone right now. It has a very weird thing that they do. So if the code is compiled to be thread safe, then it has this struct global config where it sets different functions to be the thread safe versions. So unlock when it's not thread safe is a no op. All right, and if it is thread safe, it's an unlock. And it has, this one is protected by a lock, and so on and so forth. All right? The thing is that this happens at compile time. All right? So you're like, all right, seems like a weird thing to do. They basically reinvented vtables, but only for compile time stuff, whatever. So this is the way the code works. It goes this one level of indirection to this global config struct, and then it invokes the appropriate function. So it's an indirect call. So indirect calls are cheap. Right, so sometimes people who bitch about C++ are like, oh, indirect calls. Indirect calls are pretty cheap, right? They really are. However, pthread mutex unlock is also pretty cheap. And so putting that actual, this indirection beforehand is dramatically increasing the size of the critical sections. They're small critical sections, but now they're about twice as big. And in fact, Cause highlighted all of these lines. And it said, hey, you should look at these lines. If you speed them up, you'll get some performance increase, but don't speed them up too much. So that wasn't hard. All we did was we removed the indirect at compile time, and then we got a 25% speed up. Right? I know, right? 25% speed up. The cool part here is if you look at the profiles for that code, it takes no time. Right? The amount of time that is spent on each of those indirect calls is 0.001%. You would never optimize the code without Cause telling you that that's something you should optimize. So we optimized a bunch of stuff. We had fun. We decided to attack a bunch of other stuff. We sped up memcached by about 9%, SQLite, like I mentioned, etc., ferret, dedupe, FluidAnimate. These are pretty awesome. So FluidAnimate and Stream Cluster, we sped up by 38 and 68% respectively with one line of code change. So it pointed to a custom barrier implementation that they were like, we are geniuses at Intel. We'll make the super fast, crazy barrier. And we replaced it with the default system barrier, and that's all we did. And it sped it out by. So too clever by half. All right, so you can go ahead and download Stabilizer yourself. Cause in particular is ready to roll. Like I said, it's actually going to be shipping with Debian. And with that, I'll conclude and take any questions. Thanks again for your attention. Yes?
So this looks good if you're in a pure software world by slowing down various components. But what happens if you have hardware? You want to optimize the drivers.
So what happens if you optimize hardware? So in principle, so Cause has nothing to say about this right now. We can detect issues with I/O and so on because it can still tell you if this piece of code were to run faster, then things would actually speed up your program. So it can identify areas where you can speed things up by changing software. But you're asking really, I'm not actually sure if you're asking whether it's going to diagnose problems in the hardware or if it's about software that interacts with hardware.
What I meant is that if you're relatively slowing down various components,
Yep.
you can't really slow down the hardware.
Well, I'm not sure that's true. Certainly you can slow down, so we haven't pushed on this, but you can trivially slow down, for example, network interface cards by just lowering the amount of time, increasing the amount of delay between sending things and talking to the NIC. You could do the same thing with the disk. I think speeding things up is hard, slowing things down, super easy. That is not a problem. So, I recommend everybody today go out and slow down stuff everywhere. It will be great. Yes?
So as somebody who has been doing performance optimization and characterization myself for a long time, I really appreciate it. This is really cool stuff.
Thanks.
But I have a question. You're assuming that by slowing down n-1 components, it will have the same theoretical effect as speeding up that one component. But I'm not sure. Programs don't really work necessarily that way. I can imagine that for some programs it's going to fail. For example, programs that might have 8 specific delays in them. So I'm wondering if you've thought about or maybe reached points where the predicted optimization and what you've got are not quite off, and maybe there's certain classes of programs that this might not really help or work very well.
So let's see. So that's a lot of questions to unpack. Let me see if I can answer briefly. So we have yet to encounter anything for which the predicted speedups did not actually, when we implemented an optimization, didn't actually turn out as planned. The thing is that it's not, so Cause is not super useful for a serial program. It works. It presents a kind of nice visualization of things. It's useful, but it's literally the same information that you could obtain from a profiler. It's just organized differently. When you have asynchrony or concurrency, that's where Cause really shines. And so when you say the n-1 and one thing, if you have code and there's like 5 different versions of it executing, Cause is smart enough to say, okay, we're speeding up this piece of code. It's only the other stuff that gets slowed down, right? So it's not that it's literally just one at a time. It's really a particular code fragment, and anything running concurrently with that code fragment, no matter how many threads are running that, will all get slowed down. So you get the right speed up. But other than that, I think obviously that if you have code that is not CPU bound, then there's not much you can do in a profiler. So Cause can't magically say, I will speed up your network connection to China, or maybe you should work on that. Maybe you all should work on that. But if you have code that you can speed up, so far we've been able to find some nice optimizations. So many people. I'll start in the back. Yes.
So, just to follow up on
Louder.
Just to follow up on Erez's question.
Yes.
So it's parallel code, right? You have blocks, you have timeouts.
Yes.
So when you have timeouts, what do you do?
Yeah, so that's a good question. All right, so the question is about timeouts. So it is the case that if you were to slow things down a lot, right? So I made it sound as if, for example, I have something and I speed it up by 95%. That means I'm actually slowing everything down by like 20x. What we actually do is we do it with sampling, and then we extrapolate. So we actually just sample and we slow down just for a tiny bit of time, and then we observe the effect, and then we resume at full speed. So actually you can adjust how many samples you want and you can adjust the frequency, but the idea is we don't want to perturb the runs that much. So actually the overhead of cause by default is pretty low. It's about 10%, and you could make it even lower by dialing down the frequency of sampling. Yeah, this is actually a well-known problem with other instrumentation frameworks that cause things to fail. I had this experience at Microsoft where people were doing binary instrumentation of SQL Server, and it slowed things down enough that it decided connections were actually timing out and failing, and then you had this huge probe effect. And so cause addresses this by sampling. Great question. Yes?
Maybe this is a silly question, but have you thought about the opposite? Memoizing, results and actually speeding up?
So let's see. Have I thought about memoization? Sure. Memoization is great. Memoization is tricky in a number of circumstances. There's actually some research on trying to find more memoization opportunities. When can you not memoize? When is it worth memoizing? So there are cases, obviously, where things are non-deterministic and memoization maybe doesn't work. There are cases where the cost of actually storing something in memory and retrieving it, especially these days, where memory is relatively very slow, it's actually significantly outweighs the time to recompute things. So it is challenging. It's also the case that as you increase the amount of memory you consume, you start putting pressure on other areas of your program. So I think that it's an interesting research challenge to find opportunities to memoize and do so efficiently. Yes.
I have a question regarding possibilities that you need to optimize two things to see improvements.
Yeah, great question. Right, so the question is, what about optimizing two things? Maybe optimizing one isn't enough, and there are two things that are actually entangled, and you need to optimize both to get a result. So it's actually fairly straightforward to do two things. As you can imagine, this means you have to collect more samples because you're doing two experiments. So it's a quadratic increase in the number of samples you have to take, which is fine. But obviously things get really bad as you increase the number. So really 2 is the most that we've ever considered. It's trivial to do. So far we just have 1 enabled, but it's really straightforward.
Thanks.
Sure. Yes?
Yeah. Have you tried this in systems that use just-in-time compilation? And if not, would it be hard to extend it?
Yeah, so let's see. So the question is, have we tried this in systems with just-in-time compilation? So there's some issues there, but they're not insurmountable. There's actually a group at Cornell, I think, or CMU, who implemented some prototype of cause for Java. It's not really a problem to do this in a JIT environment. It's mostly about finding the code, right? So Java is nice in that it actually exports all the debugging symbols, even for inline code and all of this sort of stuff, so it's okay. A more interesting challenge is actually for systems that don't use the same model of concurrency. So for Android, for example, or for the web, basically, well, especially for the web is nominally a single-threaded environment, and it's all event-based. So actually, one of my students is working on the browser version of Cause right now as we speak, which we call bcause, and it works. It works. So it's for a mature JIT environment that actually produces debugging symbols, so we can say this is the line of code you want to speed up, then it works. For crappy versions that don't do this, then it's just a technical challenge that we can't deal with. Yes?
If you had a long-running version fixed of an application, have
Yeah.
you looked at using stabilizer to find an improved layout and basically optimize the code?
Yeah, so we made, so actually my student Charlie has progressed with this work since leaving UMass. We made an initial version of it that we jokingly called the Noptimizer. So the Noptimizer would just insert nox and see what happened, in addition to doing this randomization of the layouts. And that worked, but there's some overhead to actually running stabilizer, so it's hard to actually overcome it. His current thing that he's doing is a much lighter weight of version of stabilizer that is coming soon, and using that actually, it's actually pretty nice. The idea is you look at performance counters. Performance counters seem to say there's lots of misses. How about you just throw up all the cards and try again? And that tends to work actually. So you get, it's not huge improvements, maybe 10%. It's not bad. It's free.
Yeah,
So, yeah. Okay. All right. Thanks again.